All right, here's part 2 of the video guide for lesson 10.2.1, picking up with the idea of conditional probability. We just finished problem C, which I explained this idea of independent, meaning that if you know something's going to happen and it doesn't change the probability of it happening, that means those two things are independent of each other. So we saw that living on campus and being an engineering major are independent of one another because you have the same probability to just live on campus as you do to live on campus and be an engineering major. And we're going to get into this idea next with part D. So I'll read it, and it says two events are mutually exclusive or disjoint if they cannot both occur at the same time. That means that the two events are mutually exclusive if P, A, and B equals 0, or that the probability of them both happening together equals 0. Meaning pretty much that if you see that if these two things do not go together, meaning that they don't have any kind of probability, that they are mutually exclusive from happening, meaning they can't happen together. So we're going to look at the events on campus and engineering to be mutually exclusive, and we're going to see if that's possible. So we're going to look at on campus would be like our A, and engineering would be like our B. And so we're going to see if the probability of A and B occurring equals 0. And so the two events on campus and engineering. And so if you live on campus and you're an engineering major, there are 6 people who live on campus and are engineering majors out of that 240 people. And so for part D, and that 240 people is coming from, in part A, we found out that there was 240 total students in this sample size. Six of those 240 students are engineering majors that live on campus. And so that's the probability of A and B occurring together. And since that this does not equal 0, I mean, it's a small number, but it does not equal 0, that means that these are not mutually exclusive. Because even though the probability is small, there is still a chance that you could be on campus and an engineering major at the same time. And that's really the big idea. We talked about independence here, and now we talked about mutually exclusive. Now, if the probability would have been 0 out of 240 students, then you would have had a mutually exclusive thing because that would have gave us 0. But we had 6 of those people being engineering majors that lived on campus. And so we do have a number there. All right, we'll move on to the last problem here. Another probability problem. I really like this one. And so it's going to be similar to the last one, just a little bit different. So we have this data collected from Mr. Rexington's high school stats class. We have males, we have females, we have males that wear jeans, females that wear jeans, and we have males that don't wear jeans and females not wearing jeans. And so what we have is Mr. Rexington is playing a game with his students. He randomly chooses a student from his class roster. If a player guesses the gender of the student correctly, the player gets an early lunch pass. Madeline is the next player. Which gender should she guess to have the greatest chance of winning the lunch pass? So really, we want to know, should she guess the student is female or should she guess the student is male? What's going to give us the better probability? And so if we go down, I'm going to just make my A down here. First, let's talk about how many students are really in this class. You have 7 plus 7 plus 5 plus 13, that whole sample space. So 7 plus 7 is 14. 14 plus 13 is 27. And then plus 5 would be 32. So there is 32 total students in class. 18 of those students are female. So this is the probability. This is probability for female. And there for male, there's also, 32 total students, and 14 of them are male. So that's the probability that you pick a male student. And so you look at these two probabilities in terms of this game, and you say, well, without the conditional probability, without knowing anything else, would you rather pick a female student or a male student? And you would rather pick a female student, or you would rather guess that the gender is going to be female because your probability is a little bit higher. Okay, and that's your basic probability. That is not conditional or independent or any of those fancy things we've been talking about today. That's just your classic probability. 32 total students, 18 are female, 14 are male, so you have a better chance picking female. All right, for part B, Mr. Rexington tells Madeline that the student that he picked at random is wearing jeans. And so now we're going to get into conditional probability because now we're given this piece of information that just might change our probability. So now that we know the student is wearing jeans, we know that 12 total students are wearing jeans because 7 and 5 is 12 students are wearing jeans. And so we have to change our probability a bit or change our sample space. And so we know 7 students are wearing jeans. We know that 12 students, sorry, my bad, not 7. We know that 12 students are wearing jeans. 7 of those students, actually I'm going to keep it in order here, so we do female first. 5 of those 12 students are female. So this is, I should write it as probability of female given jeans. And that's supposed to be a J for jeans. Sorry, my J's look bad. So 5, so that's kind of that conditional probability is probability of female given jeans. And then the probability of males wearing jeans, well, there's 12 students that wear jeans. 7 of them are males. And so that's the probability of males given you know that they're wearing jeans. Given jeans. It looks like a 5 again. I'm so sorry. All right. And so then it says, should Madeline change her guess now that she knows that the student is wearing jeans? And the answer is yes, she should change her guess because knowing that they're wearing jeans, you have a better chance at guessing male because 7 out of 12 is a higher probability than 5 out of 12. And so that's a great example, that's why I like this problem, of how conditional probability can really change because when your sample space changes, it can change the probability. All right. Now into part C, we get into this idea of association. So in a previous course, and you know what would be a good idea too, and I could throw this in here quick, is if you go to the ebook, all these words that have been highlighted throughout, the ebook will give you a link to click on them in a definition, and it never hurts to go and see the book definition of what these words mean. They do actually a pretty good job in that book of explaining it. So back to this. So in a previous course, we didn't do this, I don't think. You may have studied the association of two numerical values by analyzing scatter plots and least squares regression lines. You might have done that late in algebra, but maybe not. Associations between categorical values and variables are determined by independence. If two variables are independent, then they are not associated. And so pretty much if you can say that they are independent of one another, they're not associated. Otherwise, they are going to be associated to one another. And so it says, are the events of females and wearing jeans associated, meaning that they are those independent or not, for the students in Mr. Rexington's class today? Use the independence relationship from part C in problem 10-62 just to kind of remember how to do independence. If I hop back there for a second, what we'd see for independence is that the probability of, and this could be, I'll change it to our case, the probability that a female, given they're wearing jeans, should be the same as just the probability of the person being female. And so if I change that for ours over here in part C, we actually did most of the work already. We have, if they are independent, this should be the case. The probability of females given jeans should be equal to just the probability of the person being female. All right. Now, if these two are not equal to each other, then they are associated. If they are equal to each other, they are independent. And so we already know that PF given J, so we have PF given jeans is 5 out of 12. Is that equal to the probability of just being female, which was 18 out of 32? And I'm thinking about trying to reduce this down. but in my head, I don't think there's any way to reduce this down to make these equal to one another. So these are not equal, which means they are associated, which means that there is some kind of association between the probability of wearing jeans and being female. It's not equally likely to happen. All right, and so the last part here, it says, are the events female and wearing jeans mutually exclusive? Meaning that both of those things happening together, does that equal a probability of 0? And we'll investigate that. Looking at the events female and wearing jeans, we are looking at female and wearing jeans, and so we're working in this smaller sample space here. And the probability of, and this is, I believe, D. So it's the probability of female and jeans, which means we're combining them. Looking at is how many females are wearing jeans out of the entire sample space. So we're looking at everybody. How many females are wearing jeans out of the sample space? So 5 females, there's 32 total people, and 5 females are wearing jeans out of those 32. And so our probability is really equal to 5 out of 32. And we can say that 5 out of 32 does not equal 0. So these are not mutually exclusive. There's a lot in this lesson here today. That's the last problem I'm going to do. I think that's the last problem for us here today. There's a lot in this lesson. Like I said, make sure you check that ebook. Check some of those definitions. It never hurts to see the book definition of it. Be sure to ask me questions if you are confused about the idea of independence, confused about this idea of mutually exclusive, or even just any of this probability stuff. Where am I getting the probability of female? Where am I getting the probability of male? Be sure to ask those questions, because it's been a few chapters since we've seen it. Quite a few, actually. We did this in chapter 8 or chapter 4, and this is chapter 10. So please ask those questions. And I'm hoping these videos made sense of this lesson.